Very good afternoon to one and all present here. I welcome everyone for the second session of this FTP, national level FTP on research innovations in computers, cognition and communications. So today for the second session, we have with us our resource person, Dr. Aswani Kumar Cherukuri. Aswani Kumar Cherukuri sir is a professor from School of Computer Science Engineering and Information Science and Information Systems at VIT Vellore. A brief description or a brief introduction to the resource person. Dr. Aswani Kumar Cherukuri is a professor at the School of Computer Science, Engineering and Information Systems, Vellore Institute of Technology. As Dean, he led one of the VIT's largest schools, overseeing 4,600 students, 173 faculty members, and multiple academic and research programs. His research interests include information security and machine learning, with over 150 published papers in national and international journals or conferences. He has received multiple awards, including the Young Scientist Fellowship from the Tamil Nadu State Council for Science and Technology, Research Publication Awards from VIT, and the Indian Express 40 Under 40 Inspiring Teacher Award. He is listed among the top 2% scientists globally by Stanford University. Dr. Aswani Kumar has served as a principal investigator for multiple major research projects funded by Indian government agencies, including DST, DAE, and MHRD. Currently, he leads a project under the SPARK program of MHRD. He is a senior member of ACM, a member of IEEE, and is affiliated with several professional bodies. He serves as a reviewer and editorial board member for reputed journals and conferences, and is an ACM distinguished speaker. He is the Vice Chair of IEEE Task Force on Educational Data Mining. It is a great pleasure that Dr. Aswani Kumar Cherukuri is here with us as resource person for this FTP. On behalf of Department of Information Science, KLS Gogte Institute of Technology, and IIC KLS Gogte Institute of Technology, I wholeheartedly welcome you for this FDP, sir.
Good afternoon, sir. Thank you.
Yes, sir. So over to you, sir.
Sir, am I audible?
Yes, sir, you're audible.
Okay. So shall we start, sir?
Yes, sir. We can start.
So thank you very much, sir, for the nice introduction. And I would like to thank Dr. Srivatswa for inviting me to share my thoughts on this faculty development program. Thank you very much, sir, for this opportunity. My lecture for the next 1.5 hours would be on the topic securing the machine learning models. My presentation would go this way. I'll be talking very briefly about various machine learning types that we have. Then I will discuss about what is the threat landscape of the available machine learning models, including supervised, unsupervised, semi-supervised, and reinforcement. What is the various threats that are there? When it comes to handling the threats and ensuring the security, generally we look at the cryptography algorithms. We all know about the importance of cryptography and its relevance in the securing data. We will look what are all the various crypto systems we have and their relevancy towards machine learning. So we will talk about what is their relevancy towards machine learning. And then we will discuss about what are the various new security models that we have, and especially the need for bringing new security models. When you have the threat landscape already available for machine learning, and there are classical modern crypto systems, why we are going for new security models. And then I will provide an overview of the various modern techniques which are available for ensuring the machine learning security. So in that regard, I will be talking about homomorphic encryption. Then I will talk about secure multi-party communication. Then I will also discuss about federated learning. Then also about adversarial learning. So these are the various, the modern techniques that I will provide an overview in my lecture. Coming to the machine learning models, we all are aware about the supervised learning models that are there, essentially doing the task about classification and predictions. They are all dependent on the availability of the labeled data. So the labeled data provides an opportunity being as a supervisor towards the learning process, and the training happens on this labeled data so that a model would be trained, a model would be produced as an outcome. What are the various examples? Say, take an example. Imagine we wanted to identify whether the emails are spam emails or non-spam emails. So we are typically doing a classification. So this can be a binary classification or multi-class classification. All that is based on the labeled data that what we have. So once we have the labeled data and based on the task we have, we can go for supervised learning, and we all know about various supervised learning models we have. Then comes to the unsupervised learning, wherein which we have no labeled data, and hence in the absence of labeled data in the means we have unlabeled data. What we are trying to do is we are trying to find the patterns. So we take a function and try to minimize or try to optimize that function so that we will do training on the unlabeled data, which in turn produces an unsupervised learning model. The best example for such task is customer segmentation in the marketing domain, wherein which we don't have labeled data and we generate the segments of customers, right, based on their, say, buying patterns or whatever it is. So based on the available data, we can do it. The point is that we have unlabeled data. So we go for unsupervised learning. Best example is like, we have k-means clustering, which is an ideal example for unsupervised learning. Next, we have semi-supervised learning, wherein which we have small amounts of labeled data but large amounts of unlabeled data. So means we have mixture of both labeled and unlabeled, but we are highly skewed towards unlabeled data and very few amount of labeled data is available. In such case, we go for semi-supervised learning models. The best examples are the speech recognition tasks that what we do, web content classification. All these are all examples for semi-supervised learning tasks. Finally, we have reinforcement learning models, which are now becoming more and more popular because of their, learning ability. The learning happens through interaction with an environment, and the learning is based on receiving the rewards based on the success or failure of the training process. The best example for the reinforcement learning tasks are like training the AI agents for gaming, robotics, the current, the navigation systems, which includes the autonomous vehicles. All these comes under the reinforcement learning tasks. So these are the various machine learning models what we have at present. All these models by and large are dependent on the data that what we provide. So you have basically a training phase as well as the testing phase. So you provide the data, whether it is labeled data or unlabeled data or whatever is the data that we give to the training process, and the training process produces a model. From that particular model, during the testing process, we derive the inferences. So this is the typical pipeline, what we can call of machine learning process. Now, in this process, we notice that there are certain entities called data. There is an entity called computing. There is another entity or process called inferencing. So one is, if you go back, we have number one, data we have. Number two, we have computation. Then we have inferencing process. Now, the point is, we don't actually deal with the machine learning models. Now we are looking at as really the security aspects. Means, what is the security that we are to take care for the data, for the computation, and for the inference process. So how do you ensure security for this, the whole process? When you look at the entire pipeline of the machine learning, we said we have the training phase, we have the testing phase in which we are handling the data and we are doing the computation, we are having the inference deriving process. Now, how do you ensure or provide security for this particular entire pipeline? Typically, what happens when we say we have a data, obviously, in order to protect the data, we go for encryption. So, through the device, we are collecting the data, and the data would be encrypted. The data would be encrypted. We are referring to the model wherein which now the data is not being processed at the device, but rather at a remote place called, say, take an example, at a cloud place. So the data is sent in the encrypted way to the cloud environment or a server environment. There, the data gets decrypted, processed, and again encrypted and sent back to the node. So data is being encrypted, sent to the server or a cloud where the decryption happens and the computation happens further on the data. Then the results would be sent back to the device, and where the device again would get the decryption process done. Now, this is how the protection is happening. Now, when we say encryption and decryption, obviously we know that there are varieties of crypto systems. Popular one is the symmetric crypto system, wherein which one particular key is used for both for encryption process and as well as the decryption process. So while encrypting, a key K is used and the same key is used for a decryption process also. Such type of crypto systems are called symmetric crypto systems. When we look at such symmetric crypto systems, obviously the challenge is how both, say, take an example, sender is doing the encryption and the receiver is doing the decryption, how both sender and receiver will have the common key. This is the fundamental challenge when it comes to symmetric crypto systems. That means key exchange is the fundamental problem. Now, what to address that, researchers have, I'm sorry for the my bad throat. So researchers have introduced asymmetric crypto systems wherein which you encrypt with a encryption key and do the decryption with a altogether different key called decryption key. So KE is not equal to KD. In this process, you have a pair of keys. Say, take an example, this is sender, this is receiver. Sender has public key, private key. Receiver has public key and private key. Now the encryption happens with the help of receiver's public key, that means PUR. Here KE stands for PUR. And the decryption happens through private key of the receiver, which is PRR. Right? Since it is a public key, sender also knows receiver's public key. Excuse me. And decryption is happening through private key, so only the receiver will be able to decrypt the message. So the advantage of this asymmetric crypto system is there is no need for key exchange. No need for key exchange. That is the main advantage of having the asymmetric crypto systems. But there are some challenges with asymmetric crypto systems as well. The question is, how do we produce a pair of keys wherein which we keep one key as a public, another key as a private is the major challenge with the asymmetric crypto systems. That means key generation is the challenge, right? Of course, we don't deal with those challenges now, but I just wanted to touch about these two symmetric as well as asymmetric crypto systems. What are the various examples? Most popular example for symmetric is Advanced Encryption Standard AES. Similarly, for asymmetric systems, we have RSA algorithm, digital signature algorithm, then we have Diffie-Hellman algorithm, elliptic curve algorithms. Like that, we have several asymmetric key algorithms which are commonly used. In addition to both these algorithms, we have another popular security crypto primitives called hash functions. What is this role of hash functions? The role of hash function is to take a message M, and when you apply hash function over the message, it produces a digest. So this is a variable length message and it produces fixed length digest. What is the purpose of this digest? This happens at the sender side in order to verify whether the received message is same or not. What the receiver would do? Receiver will take the message and calculate the hash over the message and verify that with the received digest. If the received digest and calculated digest both are same, then message integrity is not changed. Otherwise, message integrity is lost. So the purpose of hash functions is to verify message integrity. Right? So these are the mainly used three crypto primitives. One is symmetric, another one is the asymmetric. Then we have the hash functions in ensuring security. So this is another slide where in which describing about various hash functions that we have. Message digest algorithms, secure hash algorithms. Again, secure hash algorithms, we have multiple variants. So the most popular widely used algorithm is secure hash algorithm 512. So the digest is of size 512, where in which it receives a length of message of 1024. Imagine if you have a lengthy message, you divide the message into 1024 blocks, and each block will produce, will be processed, and finally a 512-bit digest would be produced. And it is processed for 80 rounds of operations. And remember, there are no collisions. That means it is algorithm, the secure hash algorithm 512 is the secured hash algorithm that what we have today. Now, when you look at these encryption algorithms and connect them with the machine learning algorithms. So we talked about symmetric, we talked about asymmetric. We discussed that symmetric uses the single key, asymmetric uses the two different keys. If you look at the symmetric algorithms, these algorithms help in protecting the machine learning model weights. And also, these algorithms protect the data that what we use for training the or building the machine learning model. When the model is at rest, and as well as while transiting the data as well. Right? This is how the symmetric algorithms are helpful. Similarly, the asymmetric encryption algorithms such as RSA, elliptic curve cryptography, or Diffie-Hellman, they are all public key-based encryption algorithms. They also secures the data transmission between the machine learning components, right? And if you look at what are the various use cases, symmetric algorithms, they encrypt the machine learning model parameters before storing them in a cloud database. That is how we can use symmetric algorithms. Even we can have a combination of both symmetric as well as asymmetric algorithms. Ideally, these hybrid models are used. The symmetric algorithm is used to encrypt the data or the model parameters. Asymmetric algorithms are used to exchange the symmetric algorithm keys, like in a typical security environments, how they are used. So this is the role of encryption in terms of symmetric as well as asymmetric in securing the machine learning models. But now, when we have already these models, where symmetric, asymmetric, and all available, then why we are going for the new machine learning, new security models to secure the machine learning? For that purpose, we need to first understand what is the threat landscape in machine learning. There are a couple of threats to the machine learning models. First one is adversarial attacks, wherein which the adversarial attacks, the attackers manipulate the input data in different ways so that it misleads the models. So the best example is we change a few pixels in an image so that the machine learning algorithm misclassify cat as a dog. So you are manipulating the input data in the adversarial attacks. The attackers manipulate the input data in the adversarial attacks. There is another kind of a threats called data poisoning attacks, wherein which attackers inject malicious data into the training set so that your machine learning model performance gets degraded. So the best example is, imagine you are building a machine learning based spam filter. If that machine learning model is trained on the poisoned data, what will happen? It will allow even spam mails also as a regular mails, or malicious mails also will be categorized as non-spam emails, because attackers have injected malicious data during the training process. What is the next? Next one is model extraction. So we have trained the machine learning model, we have given the proper data, we have trained the model. Now what the attackers would do, they take the machine learning model, perform reverse engineering on a model by querying it and observing the responses. So once you do the reverse engineering, they can also try to see that how the models they can misuse or even bypass. So the best example is extracting a fraud detection model to learn so that how to bypass it, right? So this is the model extraction. Then we have privacy leaks. Imagine if the data what we are dealing is a sensitive data. So with maybe a personal information available in terms of patients related data or some personal data that is there, and say take an example, salary related details, financial related details. So these are all sensitive in nature. So the training process is based on such sensitive data. Then sensitive training data might be inferred from a model's output. So means I take the model output and infer about the sensitive data that is used for training process. So this leads to privacy problems. Privacy leakage would be a major problem. Like one side, all the countries are looking at the models such as GDPR, ensuring the privacy regulations and all that. Any leakage to the privacy leads to big problems. The best example is a face recognition system unintentionally revealing the private information about the users is a basic problem of privacy. So these are the various threats that are there to the machine learning models. Again, as whatever we have discussed, if you see here, data poisoning happens during the training process. That means before model gets deployed. Adversarial attacks happens during the inference process. That means after deployment. Again, model extraction happens during the inference process after deployment. Privacy leakages happens during and as well as after the training. Now, the question is, how do we handle it? We spoke about symmetric, asymmetric hashing algorithms, which are from the modern encryption techniques, whether these techniques are sufficient enough to handle this threat landscape of machine learning. So that is the question mark. So we need to go for different mitigation strategies, which includes, as I've said, homomorphic encryption, federated learning, differential privacy, and etc. So as I said, traditional encryption methods are very good in securing the data at rest. That means when they are stored or when they are in the communication channel. However, they have limitations when they are applied during the machine learning workflow. What is the workflow? A few seconds back, we looked at the pipeline of the machine learning models. And hence, we need new techniques like differential privacy, homomorphic encryption, federated learning, etc. This is the illustration of requirement of new security algorithms for machine learning from the threat landscape perspective. This is about threat landscape perspective. There are other perspectives also. If you look at the machine learning models, when somebody says a machine learning, we ideally think in terms of a centralized learning approach. So take an example. Imagine I have large amount of healthcare data. Can I go for a centralized learning model? How it is possible if I have constrained devices? How I will be able to handle the big data that what I have? So in such scenarios, can I go for a distributed environment wherein which my learning process happens in a distributed way? So can the models learn from the data that is distributed? Similarly, if it is so, the distributed machine learning models, what they do, they store the data on different working models in a distributed way. So, and allocate resources for the computation purpose and as well as the algorithms in a trusted way, so that you finally build the model from the data that is distributedly available across the nodes. And hence, you call it as the distributed machine learning model. There is other approach called decentralized machine learning model, wherein which you are actually dealing with independent, identically distributed data. So the data is distributed independently and identically across the nodes. Each node works on their data that is available with them in a decentralized manner. The distributed manner in the machine learning models, you are actually taking a data and then distributing across the nodes. Whereas in the decentralized, every node is responsible for collecting the data, storing the data, as well as processing the data. And remember, this data is independent and they are identically distributed. Now, in such scenarios, whether I can go for machine learning and how to handle such, what are the options? So while encrypting the data while in use is less in common practice. That means what? When I go for distributed machine learning or decentralized machine learning, encrypting the data while in use is less common in practice. It is commonly not available. That's what it means, right? So how do we handle distributed data, learning in a decentralized manner, handling the data heterogeneity, and above all that, ensuring the privacy regulations. So when I distribute my data across different nodes, so imagine I have a part of my data is here, part of my data is here, and as well as here. How do I ensure that my data is maintaining under the privacy regulations? There are no privacy leaks. How the sensitivity is maintained. So these are the questions that need to be addressed. And in that regard, as we said, classical models do not support, classical machine learning models do not support the the task that what we are looking at, and hence we go for homomorphic encryption models, security, secured multi-party computing models, federated machine learning models. It is not security, it is secured. I'm sorry for the typo. So secured multi-party computing models, federated machine learning models, and differential privacy models. We deal first with the homomorphic encryption. Just give me a moment. Is that fine, sir? Any doubts you have so far, whatever we discussed? If any of you have any doubts, please let me know. Or maybe if you can type it in the chat window if you have any doubts. Okay, fine. So first we see the homomorphic encryption models. So the concept of homomorphic encryption goes this way. It enables the computations on the encrypted data without decrypting it. That is the concept. Few seconds back, we looked at a slide wherein which we take the data from a client node. Client collects the data, encrypt it, and send it to the server. Server decrypts the data, performs the learning or build the model, and then what happens? Whatever the responses of the machine learning training, that gets encrypted and sent to the client back. So encryption, decryption, that is what is the classical scenarios. Now, with the introduction of homomorphic encryption, we are able to perform computations on the encrypted data. So that means you need not go for decryption at the computing node. So the best example, if you look at a hospital encrypts the patient data and then send it to a cloud model for analysis and then ensuring the privacy of the data. What the cloud model would do? Perform the machine learning on the data, which is encrypted data, and provide the model back to the hospital. So this is the use case of homomorphic encryption. There are different types of homomorphic encryption called partially homomorphic encryption, somewhat homomorphic encryption, and fully homomorphic encryption. What does it mean? A partially homomorphic encryption supports limited number of arithmetic operations. That means either it supports either addition or multiplication, but not both. That's called partially homomorphic encryption. We all know that while performing the operations, we all depend on arithmetic operations like addition and multiplication. A homomorphic encryption scheme that supports either addition or multiplication is called partially homomorphic encryption. There is a second category of homomorphic encryption called somewhat homomorphic encryption. What it do? It allows both these operations, addition and multiplication, but we cannot do these operations any number of times. It provides only a fixed number of times you can do addition and multiplication. Third category of homomorphic encryption called fully homomorphic encryption, which supports unlimited number of times you can do either addition and both addition and multiplication any number of times. That is called fully homomorphic encryption. So partial, somewhat, fully. So partial, either you do addition or multiplication with limited number of times. Somewhat, you can do addition and multiplication, however, limited number of times. Fully homomorphic, you can do addition and multiplication any number of times. So it provides security to the machine learning by preventing the privacy leaks. It prevents the model thefts. It also ensures that there is no data poisoning, which we have discussed as one of the threat to the machine learning models. There are numerous applications to it in terms of healthcare, in terms of handling the financial transactions, wherein which we deal with a lot of sensitive data. The homomorphic encryptions are useful. So this particular image illustrates the entire pipeline or workflow of the homomorphic encryption. So you take the data, user's data. This happens at the client node, that means the user node. So take your data, encode the data, then apply encryption process. As I said, this encryption process is happening through homomorphic encryption, right? That particular encrypted data goes to the cloud environment. Now, what cloud would do? There is no decryption. So unlike the classical machine learning models for which we need to do the decryption, homomorphic do not require a decryption process. So we apply machine learning algorithms over the homomorphic encrypted data, and we call it as homomorphically encrypted computations. So we are essentially doing computations or computing on encrypted data. So we are not doing it on the plain data computations, rather we are doing it on the encrypted data. Then whatever the results that are output of the encrypted data, the computations over the encrypted data would be sent to the client environment. Client now take this encrypted output, perform the decryption process. Now in this, now we get the decrypted results, then do the decoding and get the output done. Now if you notice, data is in the encrypted form, so there is no leakage of privacy, right? There is no privacy leaks, and data is at the client side and it is encrypted, and hence you can avoid data poisoning attacks. And even now, cloud environment also, since the data is in the encrypted form, it do not know what is the data. So there is no sensitive data that gets leaked out at the cloud as well, and computations are happening on the encrypted data. Now, to mathematically understand the the homomorphic encryption, if you look at this image, imagine my plain text is M. My plain text is M. Now, what I do is, if I encrypt this data through an encryption algorithm, and I'm applying an encryption algorithm ENC over my plain text, then I am performing operations on encrypted data. So I am writing it as encrypted data. I have the plain text, and I am performing operations on my encrypted data. Now you look at on the other side, my plain text is there, and I am applying my arithmetic operations or any mathematical functions on it. So that results in f of m. Now, if I encrypt that particular the function value, so that is e of f of m is equal to f over e of m, right? So f over f, whatever f over e of m and e over f of m both are same. That is called fully homomorphic encryption. So in such scenario here, if you see here, your data is getting exposed, whereas in this scenario, the data is not getting exposed, right? How to do that? We have various algorithms for that particular purpose. As I said, the fully homomorphic encryption, you can do both addition and multiplication operations in unlimited ways. So there are libraries for implementing fully homomorphic encryption or even partial homomorphic encryption or somewhat homomorphic encryption. Those libraries I will be presenting it at the after discussing all the other algorithms. Also I will be talking about various programming libraries so that we can integrate those libraries either with Python or Java so that our machine learning models would be secure. So this is the advantages of having a fully homomorphic encryption. Data remains encrypted during the model training process. Only the encrypted model is shipped. Now, if suppose those who want to play online, there are there are some websites that that provide the homomorphic encryption as a service. So you can see here that the client side, you are taking an image, do the encryption process, and the server side is performing the computation over the encrypted images and performing the what is the computation that has happened, applying the filters. So you have an image that I wanted to convert that image to so monochrome, or I want to apply some filters, and that filtering application process is happening at the server. Now my data is not getting exposed. When I encrypt it and send it to the server side, server has applied filter over the encrypted data, and when it received it, I decrypt at my device and I see the image with the filter. Similarly, another use case, look at the health prediction on encrypted data. On the client side, various symptoms of the patients are being considered related to skin, eyes, digestive system, or whatever it is. These symptoms are encrypted and then sent to the server side. And on the server side, the machine learning algorithm has processed the encrypted data. And hence, since it is encrypted, it cannot see the symptoms, means the input data. Now, the model is sent back in the encrypted form to the server, the client. When the client decrypts the responses, output from the machine learning model, the predictions about the patient condition, it says hypertension is this much percentage, spondylitis problem is this much percentage, thyroid problem is to this much percentage. The point is that it has used encrypted data, computation happened over the encrypted data, and the client has received the responses in the form of encrypted data, and when it is decrypted, it could get the results, the prediction results, right? So next type of technique what we have is secure multi-party computation, which provides security to the machine learning models. What is the concept? Here there are multiple parties involved in performing the computation. So these multiple parties means you can imagine that there are multiple nodes in a networked environment. These nodes are working in sync, means they are collaboratively working on a particular task, but they don't reveal their data to others. They keep their data private. Instead, they all work on a common task without revealing their private data. This is called secure multi-party computation. Now, what is the task they are doing? Probably they are doing a task which is related to a machine learning process. Let us look at one of the examples. Imagine there are banks, multiple banks. A common problem for the multiple banks is that finding the fraud risk. But each of the banks, they don't want to share their customers' data. So what they do, these banks, either from the same countries or from different countries, jointly analyze the credit card fraud or some kind of credit based fraud risk without exposing their own customer data. So this is the best example for secure multi-party computation, where in which multiple parties are involved. They all use sensitive data, their own sensitive data, but finally they come out with a risk model, but without exposing their own customers' data or sensitive data. Of course, this is the one use case. This could be on any other data where in which multiple nodes, like this is one node, this is another node, this is another node, they all have their common data, they all have their own private data, and they work on a building a common model, but they don't reveal their data. They all build a common model, right? That model would be used by anybody, but data is not getting exposed. That is the concept of secure multi-party computation. You can look at this particular scenario, where in which you have 4 nodes, A, B, C, and D. Each of these nodes have their own data. Now, ideally, you think that their data is divided into 4 parts. So each has divided their data into 4 parts. A has divided its data into 4 parts. B has divided it into 4 parts. C has divided it into 4 parts. C0, C2, and C3. And D also as well as to 4 parts. D0, D1, D2, D3. Now you see what actually each node is doing. This data is private data. When I say data that is available with each node is private data. Now, instead of sharing the entire data to the other nodes, you see here the node A has shared its some of the private data with B node. That is A1 it has shared with B node, A2 it has shared with the C node, and A3 it has shared with the D node. It has kept A0 with itself. Similarly, if you look at the node B, B0 it has shared with A node. It has shared another part, B2 with C node, B3 with D node. Similarly, the C has shared a part with A node called C0. It has shared C1 with B node and kept C2 with itself, shared C3 with the D node, like this 4th node as well. All these nodes, what they do, they build a local model or local function over their own data of the part of their own data and the data that they have received from each of the other nodes. So G has built a function GA over A0, B0, C0, and D0. B has built a function GB over A1, B1, C1, and D1. Similarly, look at D. D has built a function GD over received data from A, received data from B, received data from C, and as well as its own data. Now, the common function that whatever they wanted to build, common risk model over F, is over all these locally built model is equal to the global model of F. We have algorithms that built such type of secured models. If you observe what it is doing, each of the nodes have built their own a local model. So here GA is the local model, GB is the local model, GC is the local, GD is the local for D. Now we apply the overall model F on all these models. This results in the actual global model that need to be built over A, B, C, D. That means entire data of A, entire data of B, entire data of C, and entire data of D. Whatever the global model that need to be built over the entire data is being built on the local models collectively made together and applying the function F. This is called secure multi-party computation, wherein which, if you notice, none of the nodes have shared completely their data, right? So A has shared part of it with one node, part of it with another node, and part of it with another node. So none of the nodes will have any complete data of others. So we are able to make our data private, but reveal some part of the data only to some nodes and keep rest of the data with us. If you observe the multi-party computation and as well as homomorphic encryption computation, both appears to be same, but if you observe both concepts in multi-party computation, multiple parties jointly compute a function. They keep their individual inputs private. In case of homomorphic, computation is performed over the encrypted data without doing any kind of a decryption. If you see the privacy aspects in multi-party computation, it is happening, the distribute the computation across multiple parties. If you see there, none of the party learns any full input of the data. Whereas here in the homomorphic, you have entire data is available at the both client and server. Of course, at the server, you have only the encrypted form and you don't do any kind of a decryption, right? If you observe the computation aspects, it requires communication between the parties for secure computation because you are building the local model and finally making the global model. Whereas in the case of homomorphic, you only share the encrypted data to the cloud, make the cloud to calculate the entire model without doing decryption. Once the model is built, it is shared back. So there is no much communication between the nodes in the homomorphic encryption. So in terms of efficiency, since you have multiple rounds of communication in SMPC, and obviously it requires larger communication, and hence it is slower. If you observe what is the threats these two models would mitigate, the SMPC protects the privacy while enabling collaborative machine learning and as well as analytics. Homomorphic encryption prevents the data leakage, and you can even work in the untrusted environments because data is in the encrypted form. We have already seen some of the example use case. One of the most popular algorithm is SMPC. Locally on devices, and only the model updates are shared with the server. Means what? You are doing a decentralized. This is the example for a decentralized machine learning model, wherein which your local models or local nodes are performing the learning process, and the learned component is shared with the global model, and global model further makes the training, and the model updates are shared go back to the clients. What are the advantages? Number one, it protects the privacy of the users' data, and it reduces the data breaches, and especially it is useful for healthcare analytics wherever the sensitive data is there. And what are the various challenges involved? The challenges includes it requires secure communication between the devices, and hence, if you see here in some of the cases, you can see homomorphic encryption is coupled with the federated learning, right? It is susceptible to adversarial updates and as well as model inversion attacks. These are the various challenges with the federated models. However, it provides privacy leakages, prevents the privacy leakages, and also prevents model extraction problems, and also it addresses data poisoning problems. If you see here, it is actually kind of encrypted, distributed, as well as decentralized machine learning technology, in which the participants or the communicating computing nodes can build a local model without disclosing their underlying data, so that each of the nodes owns their own data, and hence the organizations or enterprises, they need not worry about sharing the data at a global level. And then once the model is trained at the local nodes, the parameters are exchanged through an encryption mechanism, right? So that is where actually, as I said, you have homomorphic comes into picture. Just give me a moment. I'm sorry, I'm from past few days I have severe cold and throat infection, so that's causing some problem. So this particular diagram,
Yes, sir, no
this particular diagram illustrates the federated learning. So you can see here there are multiple local nodes, node 1, node 2, and so on. So all these nodes own their own database. So each node has their own database. So D1, D2, and so on, Dn, right? Each of them cannot directly access others' data. Obviously, it is protected at their own devices. Then what happens? The global server sends an initial model to each of the devices. That is what is the first step. So server initiates the training process, and that initiation goes to the local nodes. Then these devices, independent devices, need not share their local data. Then what they do? They run the models or build the models locally with the source data that they have, right? And then once these models are built at locally, so you can see here model 1, model 2, and so on, model n, the model details are shared to the server. So remember, it is not the data that is sent, rather the trained model details. Obviously, how do you say something which is learned component? In case of machine learning, we think the model weights are the parameters that indicate the trained component. So those weights are shared to the server. What the server will do in turn is it aggregates the collected local models. then update the global model, right? So model at the server takes the input from all the local models, aggregate it, and build a global model. And then that particular global model would be shared across all the local nodes. And what the local nodes would do, they replace their local model with the global model what they get. What is the advantage of such environment? Now, this particular node has local model. Now you replace this with the global model. That means the global model learned from not only this particular data, but also with this data, with all other nodes data. Now you have the global model. Now each of these devices or each of the nodes would perform machine learning tasks not with their own local data, but also with the data that is there in the other devices. But remember, we have not actually shared the data. So the data is there with each of their nodes, and the models are built at the locally at those nodes, and the server actually has aggregated it. So it is like each of the we see that many times our students perform a kind of a combined study or a group study, where in which they share their collective wisdom. Now here is also kind of a similar process, where in which you are actually not revealing the data, you are actually revealing your wisdom, and build an aggregated wisdom, and then every node will get advantage of the global model. This is the beauty of this federated learning process. So this design helps you to get the best and the global model, which is updated from the cloud side, of course, by the local models coming from the other collaborators. So what is the main advantage is that we use our own local model to the prediction. At the same time, we use aggregated, more refined model that is also taking the learning process of the others, so that obviously it leads to the better predictions or better classification, or whatever is your machine learning output, that would be much better. So even if our device is not contributing enough to the central model, since we are part of that federated process, we are able to gain the advantage. So when you compare this process with the traditional models, so traditional centralized learning model, obviously you are dependent on the local data that what we have, right? In the distributed machine learning, where in which you are doing parallelization. Now it is also dealing with the decentralized machine learning, where in which each of the nodes are dealing with independent and of course identically distributed data. So look at this, one of the use case, right? Hospital A, hospital B, hospital C. We all know that hospitals treat their patients' data as private and secure data. So if you notice here, each of these local hospitals, they built their own local model, right? Similarly, at hospital B, their own local model, their own local model. Now these local model details are shared in the secured manner to the cloud or federated learning server, right? So which in turn aggregates and then build the global model and share it across all the hospitals. Now in this process, what happens is, you see here the step 1 local model sharing, and in the step 2 in return from the server to the federated learning server to the local nodes is the sharing of the global. Now doctors, say take an example, doctors at the hospital A will also know about the details or the wisdom or the information that is available in the other hospitals about the treatment history or about the symptoms or about the the issues that are there. But the main advantage is that you are actually not, each of the hospitals are not sharing their patients' data to the other hospitals. That is the advantage of this federated learning environment. Next, we have next model of in the securing the machine learning is differential privacy. What is the differential privacy? The concept is it adds a controlled noise to the data or even model outputs. So we are adding controlled noise. The most important term here is not noise, rather it is controlled noise. Because if you add random noise, we cannot manage the model performance. We are adding controlled noise either to the data or to the model outputs, so that we prevent learning about any specific individual in the data. So the best example or a use case is a company collecting user browsing habits, right? And it can add random noise before analyzing. Rather, actually, it is a the kind of a controlled noise. Okay, controlled noise before analyzing the trends, so that individual user behavior remains private. There are mechanisms to add the controlled noise, which includes Laplace mechanism as well as Gaussian mechanism to introduce controlled noise into the data or to the model. There are various use cases, including popular the companies such as Apple, Google. They all use differential privacy while collecting and processing and then revealing the and analyzing the various individuals' behaviors. Individual means the users of those products, whether it is a Chrome or any other Google product. While it is analyzing the user's data, Google uses differential privacy concept. Next we have is adversarial training. So adversarial training is uses concept called training the model with adversarial examples. Means we while training the model, obviously we give the data. So the data here is supplied with adversarial examples. The best example use case is the self-driving car is trained with the images that deliberately mislead, having the misleading elements, so that the model will have better handling ability so that it can manage the real world distortions. So adversarial training is done in an intention to improve the model performance. It may appear is similar to the data poisoning. Remember, adversarial training is to improve the model performance. Data poisoning purpose is to spoil the the model performance. Both are different. The purpose is different. So there are various techniques, including gradient masking, feature squeezing, defensive distillation for adversarial training. Next, what we have is people can use blockchain also for ensuring machine learning security. We all know that blockchain is a distributed, decentralized ledger. So its purpose is to record the transactions. When it is recording the transactions, it ensures a tamper-proof way. Means it is trying to provide or ensuring integrity of the records. Right? It cannot ensure the confidentiality as such if you implement blockchain without any confidentiality mechanisms, but its purpose is to ensure or provide integrity and also ensure model authenticity. how one can integrate blockchain for securing machine learning models. So the best use case is a company records every step of training process on a blockchain, so that what actually you are doing is the way the model is being built can bring a lot of authenticity to the complete training process, so that multiple benefits, including preventing the tampering with the training data. It enables secure model sharing across organizations, and obviously, as the blockchain is meant for the purpose of auditability, you are able to audit the AI decisions. So now people talk about various AI, including transparent AI, unethical, ensuring ethical AI, so that no, there is no ethical aspects are compromised, then ensuring unbiased AI. So all these things are even to audit the AI decisions or the model inferences, we can go for, or we can integrate blockchain to the machine learning process. Now, so far we have seen various modern machine learning security techniques that ensures security for machine learning. Now, suppose somebody is building their machine learning models, how they can integrate these the modern security techniques. Of course, there are libraries. For example, for homomorphic encryption, you have seal from Microsoft, which can be integrated with Python essentially, or even with C++, and it is an open source library providing various homomorphic encryption schemes. Similarly, you have the homomorphic encryption library HElib from IBM that can be integrated with C++. It is a flexible library implementing various homomorphic schemes for machine learning applications. Similarly, for federated learning, you have TFF, TensorFlow Federated, which can be integrated with the Python, and it's a framework for building privacy preserving federated learning models, and you can integrate it with the TensorFlow. Similarly, we have Flower, which is again supporting or integrated with the Python programming, and it's a user-friendly federated learning framework and supports multiple machine learning libraries. So these are the various popular libraries. Of course, other than this, we have several others under each of these these schemes, whether it is homomorphic or federated. There are several other programming libraries that can be used. When it comes to secure multi-party computation, you have MP SPTZ, which is again Python or C++. It supports various SMPC protocols, and this can be used for secure computation across multiple nodes. Similarly, ShareMind, which is again Java and C++ multi-party computation framework for ensuring the privacy preserving computations. For differential privacy, we have Google Differential Privacy library, which can be integrated with the Python or C++. Similarly, PyTorch Opacus, again for Python-based library for training the machine learning models with the differential privacy aspects. Similarly, there is a library called TRIVLIB library from IBM, which again for Python with the Python support, and it's a library for differentially private data analytics and as well as machine learning. So we can integrate these these programming libraries for our machine learning projects, as well as building the machine learning models as per our requirement. See whether I'm looking for handling sensitive data, or whether I'm looking for an application where in which multiple parties are involved, or where in which I'm looking for data which I can encrypt, but let my cloud take the entire process of building the model, and then I can only do the decryption process. So all this, based on our requirements, we can take a library, and we can choose the model and then integrate that with our machine learning pipeline. So what are the best practices for securing the machine learning model? So we can conduct a regular security audits, so that we can identify any kind of vulnerabilities, and use the the modern the security techniques like homomorphic encryption or differential privacy or SMPC, not like regular the classical like symmetric as well as asymmetric models. Rather, we can go for these the specific models for our machine learning. Similarly, we can have access control mechanism. Of course, this is on top of the models that what we discussed. We can also deploy the adversarial training techniques, so that we can strengthen the model robustness, so that as I said, instead of training the machine learning algorithm with the regular data that we have, we can also give adversarial examples, so the model would become more robust. And ultimately, we need to monitor the models for any kind of an unusual behavior anomaly, so that we can identify or indicate if there is an attack. So we all know that the machine learning is continued to be integrated in several domains. That includes sensitive data. These domains handle a lot of sensitive data, whether it is healthcare, finance, and above all that, national security data. All this data requires ensuring the privacy and providing the security is the paramount, right? So in such scenarios, while traditional encryption techniques provide a strong foundation, but modern adversaries demand advanced domain-specific security approaches. And above all that, we have seen the threat landscape. One side, because of the threat landscape that is there with machine learning models. And on the other side, we have seen that the computation requirements, not that we do computation at the local node, but we go with distributed as well as the decentralized way, right? So that is another side, we need altogether different security models than the traditional encryption models. That is the another reason why we are going for these, the techniques that what we discussed today. So techniques like whatever we discussed today: homomorphic encryption, federated learning, multi-party computation, differential privacy, they all provide finally privacy preserving machine learning models, right? So if you observe, encrypted computation can happen through homomorphic encryption. To summarize, so user privacy while training, you can go for the federated learning and differential privacy, and we can prevent the model and data leaks through secure multi-party computation and as well as differential privacy, and we can ensure that we are not sharing the raw data while performing secure collaborations, right? In future, if you observe, there would be demand for this type of models due to the process that the governments are bringing AI into their governance, right? They also wanted to regulate machine learning, and obviously you need these models when you have regulatory the laws in place, like compute only with ensuring the privacy, no leakage of sensitive data. All such governance related frameworks are there. Obviously it demands such type of security models. And we also look at the models such as explainable models, so that finally the model's performance is anyway will be good, but at the same time we will not see the model as a black box, right? At present all the models work as a black box based models. We need to bring in explainable AI models into the applications, so that your model's transparency will be enhanced, so that on what basis the decisions are taken. So when a model is taking a decision or an inference out of it, what is the basis? On what basis the model has taken the decision? So if that explainable aspects are included, and now there are some models, Shapley model, live model, like that, there are some models that also can be integrated with the the AI security methods. And obviously, when on one side the cryptographic techniques, people are talking about quantum resistance because of threats from the quantum computers that are there. On one side, the symmetric techniques have fundamentally the problem because of the Grover's search algorithm that is there in the quantum computers, and as well as asymmetric crypto systems have the fundamental threat from the Shor algorithm that is there in the quantum computers. Now people are trying to build quantum resistance cryptography principles. So in future probably people have to focus on future proofing the machine learning security also from the quantum threats, and hence you may require quantum resistance cryptographic techniques ensuring the machine learning security. With this, I would like to conclude my presentation, and if any questions are there, I would be happy to address.
Thank you, sir. Thank you for the wonderful talk. So if any participants are having any questions, please raise your hand.
Sorry, in between I have to stop a couple of times because of my bad throat. Please.
Sir, I'm Dr. Harish Kenjanawar, sir.
Please, sir.
This is really a fantastic session, sir, with the securing machine learning models. Basically, my question is here. So, in the client-server architecture or in a distributed learning architecture, so whenever we want to run machine learning algorithms, so basically, where we have to run those machine learning algorithms? Is it at the client side? Is it at the server side? Or based on the application, we have to tune such that we should get some good results?
So yeah, so the question is about when you have the client server environment. So this is my client, and you have at a server at a remote this one, and they are connected through internet. Now client obviously have the data, right?
Yes.
Now client have the data. This data may be sensitive. We assume it is sensitive data.
Yes.
Now he wanted some analytics over this data, or he wanted some machine learning model applied over this particular data. Now imagine if what we discussed so far is all about. Now imagine if the client has enough resources that he can be that he can do either analytics on machine learning at his own side, then there is no problem. Now imagine if you don't have resources, obviously you need to share this data to the server. Now the question is, he cannot share the data, rather actually he can encrypt the data and allow the server to decrypt it, so that perform computation, and then again server would encrypt the model or inference or results, right? And then send it to the client. Client will decrypt. This is the classical, so far the people talked about, or whether it is symmetric or asymmetric approaches that are there. Now the question is, if suppose I have a, as you have homomorphic encryption, wherein which you encrypt this entire sensitive data through homomorphic encryption. Now server will perform computation over the encrypted data, right? So homomorphic encryption, you are doing computation over encrypted data. You are not actually decrypting. That is the main advantage, right? Because of that, you are not sharing the sensitive data. Your sensitive data is at the location itself. You are performing computation over the encrypted data. So take an example. Uh, you know, uh, you do imagine I have two numbers, 2 and 3. I'm asking the server to add these two numbers. So 2 plus 3, and server is telling me 5. Now, what is happening? I'm encrypting 2 and I am also encrypting 3 and sharing this data to the the server. So this is say C1, this is C2. Server performs C is equal to C1 plus C2 and then reverse back C. What the client is doing? Client is decrypting the C and getting 5. Now means your addition has happened over the encrypted data. So whether I go for encryption, homomorphic encryption, I'm able to do this computation over the encrypted data. No, whether machine learning is to be applied at the client side or server side, it all depends upon my application and the resources that what I have, right? So this is the one scenario I said. If you have no resources and you have a large amount of data, encrypt it and share it with the cloud. Let the cloud perform the computations over the encrypted data and give you the results. That is how you go for homomorphic encryption.
Yes.
Now, question is, imagine I'm also wanted to learn from other clients. This is one client, there is another client, right? I want to learn not only from my own data, but also from the others' data, right? So that is about federated learning, wherein which each of the clients will not actually share their data, rather they share their models. Then you have secured multi-party computations, wherein which each of the nodes will perform local functions and then do the global function, which is working together, a collaborative environment. So it all depends upon the type of task what you have and the type of the security that what you require. Then obviously you can go for either of these models.
Yes, sir. Thank you, sir. Thank you very much, sir.
Any other participants are having any questions, please raise your hands, or else we'll wind up the session. Thank you so much, sir, for joining with us as a resource person for this national level FTP on research innovations in computers, communications, and cognitions. Despite your ill health, you have been here with us as a resource person. Thank you so much for that, sir. I thank all the participants for being here and attending this FTP on this day 1. So we'll wind up the session over here. Tomorrow's session will be starting at 10:30 a.m. in the sharp.
Thank you.
Thank you so
sir.
much.
Thank you all
Thank
the
you, sir.
participants.
Thank you very much, sir. Thank you.